All right. So I want you to consider for a moment a kid on a merry-go-round. It's going faster and faster and faster, and you might have done this as a child. Um, and what we want to ask ourselves is, how can we describe her path on this merry-go-round? Which way does she have to pull to stay on? Because as you might imagine, if she lets go, she's going to fall off the merry-go-round. So what kind of force is required for her to stay on, and how can we describe that? And then what's going to influence how hard she has to pull? So can we describe all of her motion? This is something that comes up a lot in physics, which we call circular motion. Today we're going to talk about something, a specific kind of circular motion called uniform circular motion. And when I say uniform, what I mean by that is that our speed is constant. So as you're going around the circle, you are always moving at the same speed. However, because you're going in a circle, your direction is constantly changing. Over here, you're going this way. Over here, you're going this way, and so on. And because you're always changing direction, even though the magnitude of your velocity vector isn't changing, the direction is. So if your velocity vector is changing, there has to be some acceleration. There has to be an acceleration here. And that's what we're interested in, this acceleration that keeps us moving in a circle. Um, it turns out that the acceleration that you need is in fact directed exactly towards the center of the circle. It's the force that you need, the acceleration that you need to pull you out of your straight line path onto a circle. And this acceleration will in fact always be nice and perpendicular here to your velocity, assuming uniform circular motion. And we have a special name for this acceleration that's required, and it's called centripetal acceleration. And centripetal is a fancy word that means center seeking. So it always points towards the center. You might know a very similar word, centrifugal, which is similar, except it means center fleeing. So it always points away from the center. So we have this, this acceleration that we're very interested in, this centripetal acceleration. Well, as it turns out, and there is a proof of this, but it's not particularly interesting, the acceleration that you need to keep yourself moving in a circle is exactly equal to the square of your velocity divided by the radius of the circle you're moving in, v squared over r. Now, there is another way to describe rotation, which some of you have seen before, and which we will see a whole lot later in the year, that talks about angular velocity instead. So kind of the number of radians per second you're moving. This would be, how quickly is this angle changing? And in that perspective, we get a slightly different equation, omega squared times r. We're mostly going to be sticking with v squared over r for the moment, but this omega squared r will rear its head later. So again, just to kind of pause for a second, because an object in uniform circular motion is not traveling at a constant velocity in a straight line, Newton's first law tells us that there must be a force on it. Well, how do we find a force? Well, F equals ma, right? So we take that centripetal acceleration, and now we have a centripetal force that is required of mv squared over r, and I've put lots of stars next to it because that force mv squared over r is very, very, very critical. Where does this come from? Again, this is F equals ma, so here you can see that v squared over r for our centripetal acceleration. And again, this force always has to be directed towards the center of the circle. And if we don't have that net force, let's say we don't have quite enough to get mv squared over r, what happens? Well, in that case, it departs a circular path. So imagine that we were like whirling a ball in a string and we had some tension force that was keeping it in line. Well, if that string breaks, we no longer have that tension force, and Newton's first law tells us that we would just move off in a straight line. So if that string breaks, the ball is just going to fly off. So the centripetal force, I want to be a little careful about here. The centripetal force is telling us something that has to be true about the net force of our system in the radial direction. So there has to be a net force that points towards the center of the circle, and it has to have a magnitude of mv squared over r. I do want to point out the centripetal force is not some new kind of force. You should never, on a free body diagram, have something labeled Fc. There is no centripetal force on a free body diagram. Instead, it's provided by another familiar force. So again, if I have a ball on a string, what's going to be providing that centripetal force? If I have a ball on a string, it's going to be tension supplying that centripetal force. If I have the Earth going around the sun, it's gravity providing that centripetal force. So something is always providing the centripetal force. It's never just a new kind of force. You never just have, oh, here's a centripetal force. So how do we deal with circular motion? This is the practical side of things. Well, the first thing is whenever we draw a free body diagram, and we should, there really should be a step 0 here. So I'm going to add a step 0. Step 0 should really be draw an FBD, because you always want your free body diagram. And then before you can write out Newton's second law, we have to decide what directions matter to us. So here, what we're going to do for circular motion, anytime something moving in a circle, is we have to use the radial direction for one of our directions. So we're going to choose our radial direction and then some other orthogonal direction. So for this example, right, if this is a top view of a car going around a track, well, we've got to pick the radial direction. We've got to pick an inward direction. And then we need something orthogonal to that. In this case, maybe we'll pick the tangential direction. So along the circle, maybe we'll pick z, straight up and down sometimes. And what's unique about this coordinate system that we haven't seen before is that it's not static. We're used to x and y always being x and y, even parallel to the ramp and perpendicular to the ramp for some inclined plane. Those don't change. Here, our coordinate system is always different. So that r hat vector, the unit vector that points in the radial direction, points in all different directions depending on where we are. If we choose the tangential direction, again, it does the same thing. It's constantly changing direction. You'd think that would be a big deal. It isn't. We can actually do that just fine. So we always want to pick the radial direction. Then we set up Newton's second law, as we always do. And remember that in the radial direction, you must have the net force be mv squared over r in the radial direction. Because if you don't, you're not moving in a circle. And then we do some physics with it. And then we do some physics with it. All right, so I'm going to take a quick pause and then do this first example.